we start recording again, and again, same script. As I say, if you have problem, if you have issue with the recording, please let me know before I continue and finish the recording. Okay, so what we learned so far was a simple mathematical description of joints, links, and coordination system. So we try to actually classify, we try to create a simple model of robot structure and also robot movement, okay? We need this model both for simulation, for design, and also for programming. So when you're designing a robot, you definitely need to understand that what would be the workspace, what would be the movement, style of the robot, where, what is the, how flexible, how good. Although at the moment we don't do those calculations because there are standard classified type of robots available, and you are not going to, very, very innovative robot design. But as an engineer, we should have an understanding on that. Okay, we have to have a solid understanding of robot mechanisms, actually. So the robot mechanism with coordinate frames, well, based on geometry of the robot, what we've learned so far is if you give me a sequence of joint links, doesn't matter how far you go, by using homogeneous matrix representation and coordination system representation, I can find a relationship between coordination on any point, on any location, based on any coordinating system I have on links or joint of the robot. Oh, well, what I'm saying is we can. I don't say it's easy, but I say we know how to do it. We know how to create this relationship between robots, okay? So the geometry description of the robot mechanism is based on the usage of the translational and rotational homogeneous transformation matrices. A coordinate frame is attached to the robot base and to each segment of the mechanism. So on base, we have a coordination system. On each segment or joint or link, we have a coordination system, and the relationship between these can be described as we did before. Now I want to make it more, I want to make this more straightforward, make it kind of easier to do rather than just going step by step through what we did before. More classified, okay? We are not adding new data. We just revise what we did and we try to make it more straightforward to do. Vector expressed in one of the frames can be transformed into another frame by successive multiplication of intermediate transformation matrices. Okay, so if I have address or location of one point, I can change it to address or location of that point in another coordination system using these transformation matrices multiplied one after each other. Okay. So these parameters are what we have now as parameters. Let's look back on what we have. Vector parameters for geometric description of a robot mechanism are, well, consider only mechanism with parallel or perpendicular consecutive joint axes. So what I have is we are not making random assumption for our coordination system, okay? although we're free with that. If you like, you can do any assumption for your coordination system, but it's better, it's easier if we consider only coordination system more in the home position or in the initial state of the robot. Those systems are perpendicular, axes are perpendicular or in parallel. So let's say if I have a system like this, the other system will be, other coordination system will be like this. So either in parallel or in perpendicular based on X, Y, Z, you're making assumption. We probably don't prefer, I'm not saying we can do, it's up to us, but something like completely different, just making a different kind of assumption, completely rotated like 19-degree in one direction. It's up to you if you want, but it's not suggested in this approach. We consider every coordination system in parallel with each other or perpendicular. Segments, like segment 1, segment 2, segment 3, like segment I-1 and segment I, okay, connected by joint including both translation and rotation. So between segment I-1 here and segment I, let's say here, you have a link, combination of both. Translational, because you have links, mechanical, physically connections, links, and also by rotation. Sometimes these also might rotate against each other in as a fixed rotation or variable rotation. Both are possible because the structure of the robot, for some reason, you might make your robot in a way that the links are not just straight. They might have been bended or shaped based on mechanical calculation you want for strength or or material you use in your robot. So the concept is we have joints. Joints are numbered from 0 to n. You say joint number I-1 and joint or point I. Relative pose of the joint determined by the segment vector Bn. Bi, and unit joint vector E. So two basic concepts, B and E. E is the joint vector. E is a vector, tells me like this. You see this E? This is E. Tells me what is the orientation or versus the coordination system of the joint and B is what you have in terms of length and displacement of the joints against each other. It will be more clear when I explain later. Don't worry if these are just, consider these two as two important parameters, B and E. Okay. Segment I can be translated along the vector E for the distance D, or rotate around E for the angle theta I. Okay, so you try to classify, I want to get rid of this random shape things. We want to make it more straightforward and more classified to be able to write equations more straightforward and easier rather than getting involved in detailed calculation and finding details of every angle, every length. Okay, so what we learned: B, E, E, theta. B representing the link. E is a direction, is a vector, showing what is the direction, like this. D is displacement, like this. See this small displacement, you see? Your like other robot, I have a link with joint goes up and down. And theta is the angle, as you can see here. These two are physical parameters of distance and rotation. These two are conceptual. B and E are conceptual, representation of length and guidance vector, if you like to name it, to describe orientation of the joint versus other parts. Okay, well, regarding E and coordination system, we try to keep E in parallel with one of the axes of our coordination system. So E is, we try and we do it in a way that will be parallel either with X or Y or Z. Okay, so in a joint like this, if I'm defining my coordination system as this, X, Y, Z, my E also is in this direction, or can be in this direction, or can be in this direction. How do you pick? Depending on your robot structure and which one is easier for you. End of the day, these are middle parameters. The final solution should conform with your physical understanding of the robot. You see, the coordination system of the end effector and the base should make sense. Okay, we use this EB and everything to create that relationship, and at the end, our calculation, it should make sense. But normally we choose E in the direction of Z or Y or X. Depending on which one do you choose, E might get any of these values. It will be 1, 0, 0 if it's in the direction of X. It gets 0, 1, 0 if it's in the direction of Y. It gets 0, 0, 1 if it's in the direction of Z. Okay, so remember that. During example, you see it's super easy. We are not making things complicated. We're just adding few new notation just to make it easier. Okay. B, segment vector describing the segment I expressed in X, Y, Z. So if you have length in one direction, you include it here. So length in the direction of X, in the direction of Y, in the direction of Z. So from this coordination system to this coordination system, here I have an E, here I have E2. So E1, E2 can be either, can be anything, depending on how do you choose. But from here to here, you see your B is in the direction of X, Y, Z, in the direction of Y with this much. Okay, with this length from this point to this point, this much. All right. B. Theta tells me how much in terms of angle I'm rotating. The other BI can rotate versus BI minus 1 system. So the rotational variable representing the angle measured around the E axis. So our angle will be, so if I have E, my rotation will be around E. Okay, to make it super clear, easy. Axis in the plane which is perpendicular to E. The angle is 0 when the kinematic pair is in the initial position. And finally, translational variable representing the distance measured along the direction of E. Along the direction of E, distance equal to along the direction of E, the distance equals 0 when the kinematic pair is initial position. So how much we have in terms of displacement from one point to another point. Okay. Again, don't worry when it comes to examples. You see, they're much easier than the details I'm explaining. So rotational joint. In rotational joint, so the variable is theta and displacement is 0. So from here to here, you see that there is no displacement, but there will be a rotation angle. And for translational joint, there is no displacement. There is no angle, but there is a displacement. So here, theta is 0, and we have d. Okay. And when we in initial pose, the joint angle equals to 0, and the joint displacement is equal to 0. And the coordination frame x xi, yi, zi, and xi minus 1, y and z minus 1 are parallel with each other. Okay. Any questions so far? I'm just preparing to give you another way or simpler way to write the equations. Okay. Joint axis aligned with x. Joint axis aligned with y. Joint axis aligned with z. Okay. So if your joint axis is aligned with x, means your displacement will be in the direction of x robot movement, because there are two things. B normally is fixed. D can be variable. Displacement, because depending on type of movement in your joint you have. So you see, since your joint can move along x, so you have a fixed displacement, you have a fixed translational because of the shape of the robot, which described by B, and you have translational because of movement of a joint, which you describe it by D. Okay, so for each joint here, from joint I minus 1 to joint I, you might have both translational and rotational. Okay, in translational, also you have two components. One is your fixed because of the shape and size of the robot, and one variable. Since we are assuming that joint is aligned with x, means your change in movement, translational movement, is in direction of x. That's why you have your di here. Okay, and since you are aligned with x, means your e is on x, so your rotation will be around x as well. So here what I have, rotation is around x, and also your translational movement variable is alongside x. Other changes, physical shape, are coming as b parameters. Same story goes with y. When you have y, your variable is here, and your rotation is also around y-axis. And with z, same thing. Again, your movement is alongside z, and your rotation is around z-axis. Okay? And when you have a simple link, when you joint, okay, there is no joint. You have a solid shape connection of two parts. They're not changing. You have the robot designed like this. Fixed. There is no joint. And you start from here. This is fixed. When you have a fixed without any joint, then you might have just, there's no rotation, you have only fixed translation, depending on, for example, in my case, what I said, your robot starts from here. So in coordination system, I have x, y, z movement from this point to this point. This is fixed. and we write it using star. This standard. Okay. Okay. Let's get practical. How to do now? How to use these parameters to write the homogeneous matrix for a robot, for a shape, a structural symmetrical shape of a robot. Step number one. Robot mechanism is placed into the desired initial or reference pose. Reference pose means angles are zero, variable displacements are zero, okay? So angle are zero and D are also zero. Means your robot is in initial pose, in original, before making any movement. Joint axis must be parallel to one of the axes of the reference coordinate system. So we consider our coordinate system. My robot joints and arms should be in parallel with the coordinate system. And as I said, theta, the reference pose or values of joint variables equal zero. You know that variables are those parts we change in with movement, you know, in terms of rotation or movement. Step number one, put your robot in reference pose. In reference pose. So if I give you an example or an assignment, which in the image or in the shape or in a description, your robot is moved, okay? Before your calculation, you have to put it back in the reference position, in the reference pose. Make angles and linear movements all equal to zero. Step two, center of the joints as much as half, like end joints are selected. Select where you want to have center of your joint. Doesn't really matter where you choose. Choose wisely. Choose somewhere which makes your calculations easier, right? Center of joint I can be anywhere along the corresponding joint axis. Locate coordinate frame X, Y, and Z for each joint, okay, is placed into the joint center in such a way that its axes are parallel to the axis of the reference framework. So you choose your framework here like this. Then you want to choose another based on your robot, whatever robot is. You choose the other one in a way to have axes either in parallel or perpendicular to, parallel, those are which are same in parallel with each other. That makes it easier because now we don't need to do those rotation and imagination things. You see, you remember, made it difficult. We are getting rid of most of the difficult parts, trying to simplify our approach. Local coordinate, yeah. Step three, did I read that part? Yeah. Local coordinate frame xi, xy is displaced together with the segment I. Okay. Yeah. Step three. Unit joint vector. Unit joint vector. Remember this name, unit joint vector, shown by E. Okay, is allocated to each joint axis. So for each joint, we choose one E. We pick one E for it. We define one E for it. It is directed along one of the axes of the coordinate system. You don't choose it randomly. You have to have it in parallel with. That makes your movement and rotation easier to be modeled. In the direction of this axis, the translational variable di is measured. So you have to be careful with that. How your joint moving. If you have a joint with linear movement, right, like that, define your E in that direction. With the rotational variable theta is associated is assessed around the joint vector E. And if you have rotation in your joint, define E in a way that rotation will be around E. Again, to make it easier to represent your robot model, to run your robot model. Okay. Step 4, segment vectors B, means those fixed distances, gaps, links, material, metal, whatever you have between these joints, are drawn between the origin of these X, Y, and Z frames for all segments of your robot. Segment vector Bn connects the origin of the frame with the robot point. Actually, that's what you have when you have these joints connected together. Okay. Before I go to one example, anywhere you want me to explain? Everyone is fine. Well, I don't expect you to have everything registered right now, but I'm sure after seeing the example, it will become much more clear when we do this. When we do this in terms of writing, you find it super easy, I promise. Okay, so let's have a look at this very simple example. What I have here is a robot with a shape or structure. You see. I have rotation here, as you can see, for joint 1. I have rotation here up and down. I have translational back and forth here, and also I have rotation here. Is this, is this an easy or difficult? So give me a feedback. In the scale of 1 to 10, how difficult or easy is to write the homogeneous matrix for this robot? Scale of 1 to 10. How difficult it is? 1 is very easy. 10 is, well, I can't do it. I want feedback from you, please. Go ahead. 1 to 10. If I ask you right now, start to write homogeneous matrix for the relating origin, sorry, the base to this point. In the scale of 1 to 10, how easy or difficult it is? No feedback? Shall I call you one by one? Nikita gives 11. Okay. Gino 8, Blue 9, Nasreen 9. That's it? 4 people? Others think it's very easy. Nasser 8. Did you know that the first number gives bias to everyone? It's all Nikita's fault. If Nikita would say 1, numbers would be lower. Isn't it, Nikita? It's all your fault. Actually, not hard, but not easy. Okay, so Burhan, you mean it's so you're giving like between 1 and 2? It's not difficult. Yeah. Okay. So actually, that's what I expect. Actually, that's a good thing. Means you find it difficult, and that's good. And we are introducing another method to show that how easy it could be if we follow this method. So I'll ask you the same question after we did this, right? After we did this. That's actually good. That's what, if you would say it's easy, means what I'm saying is useless. All right. So we expect that. That's very good, right? Let's go ahead. So this is a robot. What I have here is just the mechanism of the robot, the geometry and the structure of the robot, and also length and type of rotations and movements I have. But this is not a suitable pose for my robot. I have to put it in reference position, okay? In a reference position. Reference position, as I mentioned, that your translational movements must become 0. Angles, whatever angle you have, they must go back to 0 position, something like this. So step number 1. Step number 1. Set your robot or put your robot back to the reference pose, reference position. Step number 1. What was step number 2? Do you remember? Step number 2.
The center, choose the center of the joint.
Choose the center of the joints. Okay, we go ahead to choosing center of them. So I use this as my center, another, oops, center, 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 center. How many? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, different centers of that. Step number 2. Step number 2. Choose your. Do you remember what was the step number 2?
That was to choose the center of the joint.
Center of the joint. Center of the joint. We did that, and also your coordination system as well. Your coordination placed on the axis. Yeah, coordination system. So for here, I'm choosing this. For here, I have this. For this one, you see, and in a way to be parallel with each other. See, with having parallel with each other, we are making our life much easier. Okay, and this, you see, they are parallel with each other. So step number 2. So this is 1, 0, 1, 2, 3, and 4. What is the next step? Next step.
The unit joint vector.
Exactly, unit joint vector. So E. So let's choose E. And for E, well, the basic thing is I should choose E in a way that have my rotation around it and my translation in alongside it. So I'll choose E here. Rotation will be E here, though, right? And here my movement is E here, and rotation E will be like this. You know, so look at these E's we have, okay? And then we write B, theta, and D. Okay, so what I have is, so B, you see the E's we choose E1, like what we did, E2, E3, E4, like I did in the other picture, Let's write down those E's, right? Let's write down information see here, E's and other parameters for this. Okay. The way we do it is first we figure out what kind of movements we have for each joint. Let's do it first, then go with this. So joint numbers 1, 2, 3, 4. Okay, joint number 1, 2, 3, 4. Joint number 1. What kind of movement it has? Is it translational or rotation? Rotation, right? So it's angle theta 1. You see, angle. So for joint number 1, in terms of angle or rotation and translation. No translation, but there is a rotation. Here are my variables, those which change, which I have control on, which I can control using my, drive or manipulator or actuators, okay? So theta 1 for joint 1. For joint 2, I have another rotation, which is theta 2 and 0 translation. For joint 3, I don't have any rotation, but there is a displacement or translational movement, d3. And for 4, I have another rotation. I have another rotation for 4. Okay. All right. So, yeah, rotation. Now, unit vectors for them. So unit vector for joints, again, what I do will be for joints. I build a table for joint number 1, number 2, number 3, and number 4. Okay, I have E. For number 1, can you tell me what is unit vector for joint number 1? Is it in direction of X or Y or Z? Exactly, Z. It's in the direction of Z. In the direction of Z. Exactly. So in the direction of Z means I have 0, 0, 0, 1. For joint number 2, it's in the direction of X, Y, or Z. This is E2, you see? X. It is in the direction of X. So I have 0, 1, 0. For E3, which is in this direction, is E2. This is E3. It's in the direction of X, Y, or Z. In the direction of Y, 0, 1, 0. And for last one, this one, 4, is in the direction of Z, right? Again, Z will be 0, 0, 1. So first, what I did, I figured what kind of variables or movements I have at each joint. Is it rotation or translation? Then I just made it clear that what are my vectors. So these 2 steps, super easy, right? I didn't have any difficulty, honestly. Just if I have my coordinations, I can easily figure out what is E, what is changing. Is it theta or translation? So this is E vector. So this is guidance or unit vector for each joint. And the next step is just links or B part or table for B. How different centers are related to each other, unrelated to each other. Look at this. For example, so again, I make a table. A simple table for each joint, right? From joint 1, 2, 3, and 4. If I consider this endpoint as 5, I also can define that as a 5. Okay, that's what your book did. So we consider that as my general endpoint, how they're connected together. Okay, if I want to go from here to here, what should I do? I should move as B0 in direction of X, Y, or Z. From here to here, I should move B0 in the direction of Z, right? In the direction of Z. So I call this B, right? So I'm not changing my X, I'm not changing my Y, I'm just moving alongside this B0 with, length of B0 as much as it is. If I want to go from here to here, what I need to do, I need to move in 2 directions. I need to go up this much, and I need to go forward in y direction this much. In y direction and y. So sorry, I have to go back to, sorry, to this one. The length. This length is L1. This length is L2. This length is L3. This length is L4. So I need to remember that. And this one is H1. This one is H2. So I have to correct myself. All right. Okay. So this is H0. Okay. Is it H0? So L1, so not on X direction, but I have L1 and H1. Okay, this is H0, this is H1, this is L1, this is L2, this is L3, and from here to here is L4, based on what I saw, if I remember correctly. And for 3, from here to go to 3, if I want to go from 2 to 3, I have to continue moving without any change in X, without any change in, any L1, yeah. And without with L2 in the direction of Y and 0. No change in Z. And from 3 to 4, again, I have to do 0, L3, and 0. Okay. And from here to here, what I need to is just again moving 0, L4, and no change in terms of 0 if I have it in the same direction from here. If I ignore this, and well, I don't have any well, if I have something here, I have to do that as a probably negative or a value which you consider. Okay, from 4 to, yeah, I think it's a mistake actually,
3 to 4.
because yeah, exactly, yeah, it's from 4 to this one. Yeah, I made a mistake here, from here to here. So I have to consider that as I don't remember how much was it, but it was, I think we considered that as B3, if I remember correctly, the original shape.
Looks like H3.
Yeah, H3. I missed that, sorry. So here, this one will be H3, but negative. It's coming down. So again, super simple. The only thing is I need to make another table showing physical or geometrical relationship between those center of joints as we had. Just basically to see how much you're moving in direction of X or Y or Z, and you can in here. So I hope we didn't do any mistake. This is correct. Same thing, L2, oh yeah, this one is correct as well. Okay, good. So that's what I have. Based on my structure, based on my robot physical and geometrical representation, I have this relationship between base and my end effector coordination system. This is not homogeneous matrix. These are just 3 tables which you can easily build up for any robot. The next step is to build a homogeneous matrix based on these three tables. Just simply what we do is we are building homogeneous translational matrices to go from base to the end point, from 0 to 1, 1 to 2, 2 to 3, 3 to 4, and to 5 at the end. Okay, so From 0 to 1, H0 as well in the book it says 0 to 1. From H0 to 1. Look at this, from 0 to 1. What do we have? 0, 0, 0, 1. I have to figure out how much translation and what kind of rotation I have. Okay. Is there any translation from 0 to 1? As you can see, we have just one translational move as H0. That's it. So we are not moving or we are not changing in terms of coordination system. We have just increase of height H0. So it will be 0, 0, H0. As simple as that. And in terms of rotation, I have only one rotation, which is variable. It's not a fixed rotation, as much as theta. In what orientation? Around what axis? Around z axis. So what do you have here is rotation with around z with theta, which you already know what is it, right? Which you already know what is it. So if I want to write it, well, technically what I have for H1, it's H01, okay, it will be a rotation or translation, multiple rotation. So rotation around z with angle of theta times translation of 0, 0, 1, which is this. Cosine sine, this is rotation around z, so rotation around z with the angle of theta, and this is translation because I have that translation here. From joint 1 to joint 2, from joint 1 to joint 2, again I have a rotation, no translational movement. Well, variable, I mean these are variables in terms of variables, but the fixed one is L1, H1. So what I expect is, and the rotation will be around x-axis. So what I have is rotation around x-axis, with angle x-axis. This is theta 1 with angle theta 2. X-axis with angle theta 2, and translation, which is T of 0, L1, H1, which, right? Translation, rotation. From for homogeneous matrix from 2 to 3, there is no rotation. Rotation is 0, but I have a linear or translational movement, right? Like that. And well, this is alongside y-axis, and also I have fixed L. So my matrix will be only translation of 0 and L2 plus D3 or minus D3, depending on how do you define it. See, no rotation, and your translation is like that. And for 3 to 4, H3 to 4, again I have rotation. Again, it's around Z. Okay, so I have rotation around Z with angle theta 3, theta 4. I'm sorry, yeah, theta 4. Here is theta 4, and also translation I'll move alongside y, and z is 0, L3, and negative H3, which gives me this matrix. L3, negative H3, this is the translational, and this is my rotation. Okay, and finally, to the last part as we did, so which is H5, there is no rotation, there is only one fixed, or constant matrix, means no rotation, no variable, only L1, which is length of your end effector going out of your matrix. Now you have these three, just one matrix multiplication, and gives you the relationship between joints. This helps me to, well, by this actually classifying or simplifying our calculation, we should be able to do that for every robot. Again, so if instead of that robot, I have this robot, again, I can follow. First step, reference pose, and look at dimensions and sizes you have, okay? So second step, centers of the joints. Third step, coordination. Third step, E vectors. E vector. So for this one, E will be this. It's E1. For this one, E will be this. E2. For this one, E will be this. Okay, and I have sizes and I have everything else. Now I write matrices for variable, for E, and for B. Three tables, not matrices. 3 tables. Table for variables, which here I have only theta 1. For this one, I have theta 2. For this one, I have, what do you call it? Is it D3 or, displacement of, yeah, D3. D3 here. So theta 1, theta 2, D3. 3 variables. So table number 1, variables. So theta 1, theta 2, D3. Theta 1, theta 2, D3. Table 2, table 4, unit vectors, E. All 3 are in Z direction. Well, here is negative because it's defined, the author doesn't agree with us. They defined it, their E in this direction, not in that direction. They just pick their E as this, which I don't believe it makes any big difference, because it's just how do you look at, you believe that your end effector moves up or moves down based on what which way you consider. Okay, that's the only difference. And then the joints, as you could see here, the sizes, you see it's L1, L2, L3, right? L1, L2, L3. So what I have in terms of sizes, I have L1 in Z direction, L2 in Y direction, and L3. So this is L1, this is L2, this is L3 in direction of different. So using D3, I can write my homogeneous matrix again. I can write them again. So based on that, from 0 to 1, I have rotation. That's why I have rotation around Z axis. So what I have is rotation around Z with theta 1. And also I have displacement or translational movement with displacement as L1 in Z direction. So that's why I have Z here. So 1 rotation and times t of 0, 0, L1, which gives me this. For 2, I again have rotation around Z, but this time I have a translational displacement fixed, not variable, as L2, which means rotate around Z and theta 2 times translational of 0, L2, and 0, which gives me this. And for the third one, I don't have any rotation. It will be just a linear or translational movement with D3 alongside negative Z, and also a fixed length B alongside Y again. So what I have is a translational of, I don't have anything on X, I have L3 for Y, and I have negative D3 for that, which gives me this. Your final matrix is just multiplication of these 3 together to get your final homogeneous matrix representation of the robot. So I'll stop here, and well, I hope that makes your approach more clear and you understand better. For any robot, I'll give you assignment on this. For any robot, just follow the steps: reference pose, center of joints, coordinations for each joint, E vector for each one, then write the tables. Write the tables based on that. Tables, you have to write variables. You have to write E vector, and you have to write B vector to have them. When you have these vectors, you don't need to refer your robot again to see details how and why. You build up this table based on physical representation of your robot, geometrical representation. When you have it, using this, you can easily get each part of the transformation and finally combine them together to get this one. Any question?
No.
Okay. Well, I hope everything is fine with these calculations, and well, I upload assignments also. Go through them. Try. Well, we found this before with other students, pretty straightforward, because what you have is just simply filling the table and building the matrix based on the table. So what I do, I'll give you in the assignment in both ways. You know, the other, which we did, we just calculation how each is related with those basic robots, and also with the matrix and table to do a practice and see the differences. Any question for me? So I'll stop recording.